The world's greatest stone monuments are a magnificent lie. We see the finished temples and towering statues, but we are missing the true story. These wonders are not just feats of engineering. They are the final, polished product of an ancient industrial revolution, a hidden world of logistics, planning, and staggering human effort unfolded long before the first block was ever set in place. And the only place we can see that world is where it was suddenly abandoned. This journey will show you the true, breathtaking scale of ancient ambition by exploring the quarries where it all began. You will understand how entire societies were organized not around magic, but around the cold, hard science of moving mountains. How did planners coordinate thousands of workers for decades? What colossal mistakes did they make that we can still touch today? The answers are written in stone, in the scars of unfinished work. When you see a perfect pyramid, what do you truly think was its greatest achievement? But what does it truly mean to build on a megalithic scale? We often think of it as just a measurement, a simple matter of big stones. Yet the real definition is not in the final product, but in the first decision. It is a mindset, a specific and deliberate choice by a culture to engage in the most difficult form of construction imaginable. It begins with the intentional selection of a specific stone, often from a specific sacred site or a quarry known for its superior quality. It then demands the controlled extraction of a block weighing not hundreds but thousands, sometimes tens of thousands of pounds, and it commits from that very first moment to moving that immovable object across impossible distances. This is the industrial chain. The polished temple at the end is the beautiful facade. The raw, chaotic, and brutally scarred landscape of the quarry is the truth of the beginning. To walk through one of these ancient quarries is to witness organized chaos frozen in time. You see the precise cuts where a block was successfully freed, lying next to the jagged, failed fractures where the stone betrayed the workers. You see the trenches they carved around a future column and the pathways they cleared to drag it away. This is the dichotomy we must understand. The serene, perfect monument in the city center represents order, divinity, and completion. The quarry represents the gritty, violent, and uncertain process of creation. It is the factory floor of the ancient world, and it is here that we see the megalithic mindset not as magic, but as a colossal logistical undertaking. The true scale of their ambition is not measured by the height of the pyramid, but by the volume of the hole they left behind. This frozen moment is precisely what makes an abandoned quarry so priceless. A finished temple is a masterpiece, but it is also a clean slate. The scaffolding is gone, the ramps dismantled, the thousands of tool marks smoothed over by the final polish. It presents only the answer, not the working. An unfinished quarry, however, is the ultimate time capsule. It is the ancient workshop caught mid-stride, preserving not just the goal, but the entire messy, brilliant, and sometimes flawed process of getting there. Here, the logistics are laid bare. You can see the exact sequence of cuts made by the workers, revealing their standardized toolkit and the specific techniques passed down through generations. You can trace the pathways they carved through the bedrock to haul a block out, a permanent record of their transport strategy. Most tellingly, you can find their mistakes. A crack that appeared as they were undercutting a 100-ton obelisk, forcing them to abandon it. The misplaced wedge hole that split a prized column in two. These are not failures, they are data points. They show us the limits of their technology, the very real risks they faced, and how they adapted when nature did not cooperate. A completed site tells us what they achieved. An abandoned quarry shows us how they thought. It is the difference between reading a published novel and finding the author's handwritten drafts, complete with crossed-out paragraphs, margin notes, and coffee stains. The drafts reveal the true struggle of creation. So when we stand in these vast, scarred landscapes, we are not looking at a forgotten failure. We are being given a privileged tour of the ancient industrial floor, with every tool left exactly where it was set down, every plan still etched into the stone. What do these frozen blueprints tell us about the mind of the ancient project manager? The clearest window into this ancient industrial mindset lies not in a temple, but in a colossal mistake. In the sun-baked granite quarries of Aswan, Egypt, rests the most instructive failure in human history, the Unfinished Obelisk. Had it been completed, it would have been the single largest piece of stone ever shaped by human hands, a needle of solid red granite stretching 137 feet long and weighing an estimated 1,180 tons. That is heavier than 200 full-grown elephants. Its very conception was an act of breathtaking ambition, a statement in stone meant to pierce the sky. But the obelisk never left its birthplace. Deep into the extraction process, a fatal flaw appeared in the bedrock, a crack that ran through the precious stone. The project was instantly, irrevocably abandoned, and in that moment of abandonment, the ancient workers gifted us an unparalleled classroom. Every single step of their process, from the initial layout to the final undercutting, was frozen in the granite. We can walk around its massive form, tracing the trenches they carved to isolate it from the living rock. We can see the precise rows of holes where teams of workers hammered in wooden wedges, which they would soak with water to expand and fracture the stone along clean lines. We can even see the marks of their tools, the dolerite pounders harder than granite, that they used to painstakingly smooth the sides. This isn't just a broken monument. It is a complete, three-dimensional blueprint of Pharaonic engineering and project management. The crack that doomed it is not a sign of weakness, but a stark lesson in the unforgiving physics these planners battled. It shows us the immense risk they accepted every time they committed to such a titanic endeavor. One hidden flaw in the earth, and decades of planning and labor could vanish. So what does this frozen project tell us about the people who orchestrated it, the unseen managers who commanded this symphony of stone? The Unfinished Obelisk is a textbook left open to the most important chapter. Every mark on its surface is a sentence, and every trench around it is a paragraph detailing a precise and brutal methodology. To understand their process, you must first look down at your feet. Surrounding the massive form of the obelisk is a deep, narrow channel cut straight down into the solid granite. This was not a random dig. It was the first and most critical phase, the act of defining the object itself. Teams of workers, using nothing harder than balls of dolerite stone, would have stood in this very channel, swinging these pounders for months, maybe years, to carve a three-sided trench around their chosen block. This isolated the future monument, creating its shape while it was still part of the living bedrock. The sheer volume of granite dust produced is almost unimaginable, a constant cloud hanging over a landscape of relentless percussive sound. But how did they plan to free it from the earth? The answer is written in the walls of the trench itself. Look closely, and you will see rows of small, rectangular holes carved at regular intervals along the base. These are the key to the entire operation. Once the trench was deep enough, workers would insert dry wooden wedges into these slots. Then they would pour water over them. As the wood absorbed the water and expanded with tremendous, silent force, it would create a controlled fracture along a straight line, cleanly separating the bottom of the obelisk from the bedrock floor. It was a brilliant application of simple physics. This process of undercutting was the final, most delicate act. One mistake in the placement of a wedge, one unseen flaw in the stone, and the entire project could shatter. And at Aswan, that is precisely what we see. The crack that doomed the obelisk likely appeared during this undercutting phase, a hidden weakness in the earth that no amount of human skill could overcome. The evidence left behind is so complete that archaeologists can literally replay the last day of work. The dolerite pounding stones are still scattered around the site, dropped exactly where the workers set them down when the order came to abandon the project. The trenches are frozen at their final depth. This allows us to reverse engineer not just the how, but the who. The scale of the trench, the systematic placement of the wedge holes, the sheer number of pounders, all point to a highly organized workforce operating in shifts. It was not a chaotic mob, but a disciplined assembly line of stone. Each team had a specific task, from the initial layout artists who marked the perfect rectangle, to the trench diggers, to the specialists who carefully placed the expansion wedges. This abandoned site, therefore, is more than a failed monument. It is a time-lapse photograph of ancient industry, capturing the moment the whistle blew and everyone went home, leaving their tools and their ambition embedded in the rock. But if this was the factory floor, who was the manager in the corner office, who held the blueprint for this mountain-moving operation? The story of the unfinished obelisk is not an isolated incident. It is a single, spectacular page from a global manual. From the mountains of Peru to the volcanic slopes of a remote Pacific island, ancient cultures made the same deliberate, staggering choice to build with mountains. And in every case, they left behind the same crucial evidence, their own version of the Aswan quarry, where the process is laid bare. In the Bekaa Valley of Lebanon rests the Baalbek megalith, often called the stone of the pregnant woman. This single block of limestone weighs an estimated 1,200 tons, making it even heavier than the Egyptian obelisk. It was cut and perfectly shaped, but never moved from its quarry bed. Just a short distance away lies an even larger block, partially extracted and abandoned. These stones were meant for the mighty temple complex of Jupiter at Baalbek, a site built upon even older megalithic foundations. Their presence tells us that the engineers here were thinking on a scale that rivals, and in some cases surpasses, the ambitions of the pharaohs. They mastered the cut, but the challenge of the move remained. Across the ocean, high in the Andes, the Inca fortress of Ollantaytambo tells a different part of the same story. Here, the quarries are not in a flat plain, but on a mountainside opposite the temple site. Enormous red granite blocks, some weighing over 50 tons, were extracted, shaped, and then somehow transported down a steep slope, across a roaring river, and up another slope to their final position. The pathway itself, a carefully constructed ramp and road system, is still visible. At the quarry, you can see blocks in every stage of completion, some just rough outlines, others nearly ready for transport, showing a clear, step-by-step production line. Then there is perhaps the most haunting workshop of all, Rano Raraku on Easter Island. This is the birthplace of the iconic Moai statues. Walking among the slopes of this volcanic crater is like entering a factory that was shut down at lunchtime. Nearly 400 statues are still there, in every conceivable state, from mere outlines just beginning to emerge from the rock to completed figures that stand poised on the slopes, looking inward as if awaiting their final command to walk to the coast. The ground is littered with the stone picks called toki that were used to carve them. This site captures the entire life cycle, from raw material to finished cultural icon, all frozen in place. So we have a pattern, a recurring global signature. Egypt, Lebanon, Peru, Easter Island, cultures separated by vast oceans and millennia, all engaging in the same megalithic logic. They all established remote industrial quarries. They all developed standardized extraction techniques. And they all faced the same ultimate Herculean challenge, the logistics of moving the immovable. This raises a profound question. If these quarries are the shared starting point, what common principles of ancient engineering and labor management do they expose? What universal rules did these cultures discover, often through trial and catastrophic error, about how to move a mountain? This pattern of global ambition finds one of its most extreme expressions at a site known as Baalbek. Here, in modern-day Lebanon, a Roman temple complex dedicated to Jupiter sits atop a foundation that has puzzled engineers for centuries. The platform is built from some of the largest, most perfectly fitted stones ever used in construction. 3 of these, known as the Trilithon, are a breathtaking sight. Each block is a staggering 63 feet long, 14 feet high, and 12 feet wide, with an estimated weight of around 800 tons. They are placed side by side, 20 feet above the ground, with joints so precise you cannot slide a piece of paper between them. This alone is a display of engineering that seems to defy the era. But the true revelation, the clue to their impossible scale, lies 600 yards away in the ancient quarry. Here rests the stone of the pregnant woman, a fully cut monolith that was never moved. It measures 69 feet long, 16 feet wide, and 14 feet high, weighing an estimated 1,200 tons. It is the largest known stone ever cut by human hands. And just beside it, embedded even deeper in the quarry bed, lies its sibling, a partially extracted block that is even larger. These abandoned giants are the key to understanding the entire operation. The quarry is on a slight incline, roughly 30 feet higher in elevation than the temple platform. This was not an accident. The planners chose this specific location because it provided a crucial, if terrifying, advantage. They intended to slide these 1,000-ton blocks downhill. Imagine the scene. After years of cutting and shaping, the monolith would be perched on a prepared bed of smoothed earth or timber. Teams numbering in the hundreds, perhaps thousands, would pull with ropes, while others used massive levers to inch it forward, controlling its descent with a system of anchored ropes acting as brakes. One lapse in coordination, one snapped rope, and the stone would become an uncontrollable avalanche, crushing everything in its path. The very existence of the 2 quarry blocks suggests this nightmare scenario may have occurred. Perhaps the engineers attempted to move the largest one first, and a catastrophic loss of control forced them to abandon the entire approach, leaving the smaller, though still unimaginably heavy, stone of the pregnant woman behind as a permanent testament to the limits they encountered. The placement of the quarry, therefore, is a masterclass in ancient logistics. It reveals a cold, calculated understanding of physics. They were using gravity as their primary engine, turning the landscape itself into a tool. But it also exposes the razor-thin margin for error. At Baalbek, we see not just the triumph of the 3 perfectly placed Trilithon blocks, but the sobering, silent evidence of the one that got away. This forces a new question. If gravity was the engine, what was the fuel that powered these projects? What kind of social machine was required to coordinate such perilous, decade-spanning endeavors? While Baalbek shows us the terrifying physics of moving a mountain, another quarry reveals a completely different, yet equally brilliant, logistical strategy. On the remote slopes of Easter Island, the volcanic crater of Rano Raraku is not just a source of stone. It is a factory floor that was sealed shut, preserving every single step of production. Here, the iconic Moai statues were not merely quarried as raw blocks. They were born. Walking into this crater is an experience that defies time. You are surrounded by nearly 400 stone giants in every conceivable state of being. Some are mere outlines, faint sketches of a face and torso emerging from the cliffside rock. Others are half-revealed, with their elongated noses and solemn brows clearly defined, still fused to the mountain that birthed them. Further along, you find fully carved figures standing upright in prepared niches, their backs still attached by a thin spine of stone, as if waiting for the final cut that will set them free. And finally, there are the completed moai, detached and standing on the interior slopes, gazing silently across the crater. This is the sculpting phase, captured in stunning, 3-dimensional detail. The logistical genius of this approach is profound. By carving the statue completely in situ, right where the stone was found, the Rapa Nui people solved a massive problem before it even began. They transformed an impossibly heavy, irregular block of volcanic tuff into a known, balanced, and streamlined object before it ever had to be moved. Think of the difference between transporting a rough, jagged boulder and moving a smooth, aerodynamic sculpture. The former would catch on every bump and rut, requiring constant adjustment. The latter, with its defined shape, could be controlled, rocked, and walked with far greater precision. The evidence for this process is everywhere. The ground is littered with thousands of basalt stone picks called toki, the very tools used to peck away the soft volcanic rock. You can see the pockmarked texture their work left on the unfinished statues. You can follow the carved pathways or roads that lead down from the quarry to the coast, pathways worn smooth by the passage of countless stone figures. This site makes one thing undeniably clear. The Rapa Nui did not see this as a quarry in the Egyptian sense. They saw it as a sacred nursery. Each moai was individually awakened from the living earth, given its features and its spiritual essence right there on the slopes, and only then was it considered ready for its journey to the shoreline to watch over the people. This decision to sculpt on site was a monumental logistical choice that minimized risk during the most dangerous phase of transport, but it also created a haunting snapshot of a society's ambition, frozen at its peak. The factory was shut down with its inventory still in progress, leaving us to wonder what final command was never given. The logistical puzzle of Easter Island, however, pales before the sheer physical audacity of another ancient workshop. High in the Peruvian Andes, clinging to a mountainside at an altitude that steals your breath, lies the fortress of Ollantaytambo. Its terraces climb like giant stone staircases, and its temples are built from colossal blocks of rose-red granite. But to understand this place, you must turn your back on the fortress itself and look up across the deep gorge of the Urubamba River to the distant peaks. There, on the opposite side of the valley, are the quarries of Cachacota. This was not a convenient source of stone. It was a deliberate, almost defiant choice. The Inca needed a specific type of granite for their sacred structures, and they would go to the ends of their earth, or rather the top of their world, to get it. The quarries themselves are a landscape of suspended ambition. Enormous blocks, some weighing over 50 tons, were precisely cut and shaped right where they were found. You can see the negative spaces left behind in the mountain, the exact outlines of the missing giants, but the most telling evidence is not at the quarry's peak. It is scattered along the treacherous path down. As you follow the ancient transport route, you encounter abandoned mega-blocks, some partially shaped, others seemingly ready for the journey, left stranded on the steep slopes. These are not failures of extraction, but monuments to the move. Each one represents a point where the immense challenge of logistics overcame the will of the builders. Imagine the task. First, a block is freed at an altitude of nearly 12,000 feet. Then, teams must maneuver it down a precipitous mountainside, using a system of earthen ramps, rope guides, and sheer manpower. Next, they must cross the roaring Urubamba River, likely using a temporary bridge or a clever system of pontoons. Finally, they must drag it up the opposite slope to the construction site. This was a multi-stage, high-risk operation that required flawless coordination across a vertical landscape. The presence of those abandoned blocks along the route speaks volumes. They are the ancient equivalent of a snapped cable or a failed brake, a moment where the cost or danger became too great, and the stone was simply left where it stopped. This reveals a critical aspect of megalithic logistics, the concept of a sacrifice zone. Not every block was destined to arrive. The planners likely calculated a certain rate of loss, accepting that some of these mountainous fragments would become permanent casualties of the journey, marking the trail like grim mileposts. The altitude adds another profound layer. Working at such heights with reduced oxygen makes every physical task exponentially harder. It slows movement, clouds judgment, and drains energy. That the Inca pursued this endeavor anyway tells us this was not merely construction. It was an act of spiritual and political will, a demonstration that their authority could command the very bones of the mountains, no matter the earthly cost. So we see a pattern emerging from these global quarries, a pattern not of magic, but of immense, calculated effort and inevitable loss. But if these sites show us the raw effort, what do they tell us about the minds that orchestrated it all? Who were the unseen project managers of the ancient world? The silent giants left behind in quarries across the world all begin with a single, critical decision. Before any tool ever touched stone, an ancient engineer had to solve a problem that still challenges us today. Where do you find a mountain that is willing to be moved? This first step, the prospecting and geological assessment, was the true foundation of every megalithic project. It was not a matter of simply using whatever rock was nearby. It was a deliberate search for a material with the perfect balance of properties, a search that required a deep, almost intimate understanding of the living earth. Think of it as ancient materials science. If you were building a monument meant to last for eternity, you needed a stone that could withstand millennia of weather, war, and wear. Granite, with its interlocking crystal structure, offered incredible durability and a majestic, speckled appearance. This is why the Egyptians traveled to the specific quarries at Aswan, why the Inca sought out their distinctive rose-red granite in the high Andes. They were investing in permanence, but granite is brutally hard, requiring endless pounding with even harder stones to shape it. For different needs, a softer, more workable stone was chosen. Limestone, which could be cut with copper saws and smoothed with abrasives, was the perfect canvas for the detailed reliefs that covered temple walls. The choice was always a trade-off between the ideal material and the immense effort required to master it, yet finding the right type of stone was only half the battle. The true skill lay in reading the landscape itself. A perfect-looking outcrop could be useless if it was riddled with hidden cracks, fissures, or weaknesses. Ancient prospectors had to become geologists, scanning cliff faces and bedrock for natural fracture lines, known as bedding planes or joints. These natural seams in the rock were not obstacles, they were gifts. A skilled planner would look for a site where the stone naturally wanted to break into large, rectangular blocks. At Baalbek, the limestone deposits exhibited these clean, horizontal layers, which is why they could even conceive of cutting 1,000-ton monoliths. The quarry at Aswan was chosen not just for its red granite, but for a specific zone within the granite formation that was relatively free of the devastating flaws that later doomed the Unfinished Obelisk. This geological foresight was a form of risk management. Selecting a quarry with favorable fracture patterns meant less wasted labor, fewer catastrophic failures during extraction, and a higher yield of usable stone. It turned the chaotic forces of nature into a willing partner. When we look at these quarries today, we are not just looking at holes in the ground. We are looking at the results of a sophisticated intelligence, a mind that could walk a barren hillside and see within it the hidden architecture of future temples. They were not fighting the mountain, they were listening to it, learning its language to ask for its strength. And once they found the perfect source, the real work, the orchestration of human energy on an unimaginable scale, could finally begin. This profound geological insight was then met with an equally brilliant application of force. The common image of ancient workers chipping away at stone with simple bronze chisels is a dramatic undersell. The reality was a masterful application of physics, using simple tools in devastatingly clever combinations to convince solid rock to break exactly where they wanted. Think of it not as carving but as controlled fracture. One of the most widespread techniques was the use of fire and water, a process known as thermal shock. Workers would build a roaring fire directly against the rock face they wanted to split, As the intense heat expanded the surface layer, they would suddenly douse it with cold water. The rapid, violent contraction caused the superheated stone to crack and spall, weakening the structure and allowing large flakes to be pried away. This method was less about precision and more about bulk removal, a way to rough out the initial shape of a block from the living mountain. For the precise, clean breaks needed to free a perfect monolith, they turned to a quieter but equally powerful force, expansion. This is the technique forever memorialized at Aswan. Workers would carve a series of carefully spaced holes along a desired fracture line. Into these holes they would drive dry wooden wedges, then they would pour water over them. As the wood absorbed the moisture and swelled, it generated immense, relentless pressure, thousands of pounds per square inch, forcing the rock to split along a perfectly straight plane. It was a silent, patient form of demolition, harnessing the natural properties of materials to do the brutal work. This reveals a deep, practical understanding of material science. They knew wood expanded when wet, they knew stone would fracture under sustained pressure, and they engineered a system to combine those facts. Once a block was outlined and undercut, the final act of liberation required raw mechanical advantage. This is where levers, rollers, and ropes entered the stage. Using massive timber beams as levers, teams could lift one edge of a multi-ton block just enough to slip wooden rollers or a smooth clay slurry underneath. From there, it became a matter of traction and patience. Hundreds of workers pulling on ropes, coordinated by rhythmical chants or drumbeats, could inch the stone forward. Quarry floors themselves became part of the machine, with smoothed pathways and prepared ramps guiding the stone's journey from its birthplace. So when we look at the clean, geometric trenches surrounding an abandoned monolith, we are not seeing the marks of random hacking. We are reading a technical manual. Each tool mark, each wedge hole, each smoothed ramp is a calculated step in a process that transformed chaotic natural force into directed industrial power. They were not just moving stone, they were conducting a symphony of physics. But to orchestrate that symphony, you need more than tools, you need an army. How did ancient societies mobilize, feed, and house the thousands of hands required for such decades-long campaigns? The choice of how much to shape a stone at the quarry was a strategic calculation, a logistical equation every ancient engineer had to solve. Do you finish the work at the source, creating a masterpiece that must then survive a perilous journey? Or do you move a rough, anonymous block, saving the delicate work for the safety of the construction site? The answer was never the same, and the quarries themselves reveal why. Each culture made a different trade-off between transport weight, risk of damage, and the organization of on-site labor, and their choices are permanently etched into the stone they left behind. On Easter Island, the Rapa Nui chose the path of completion. By carving the moai statues entirely within the quarry, they transformed a chaotic volcanic mass into a smooth, aerodynamic, and spiritually complete figure. This was a brilliant risk mitigation strategy. The most vulnerable part of the statue, its intricate facial features, elongated ears, and detailed hands, was finished in the controlled environment of the nursery. Once it was time to move, they were transporting a known, balanced object. Any damage incurred on the journey would be to the back or base, areas that were less critical, and could be repaired or hidden when the statue was erected on its coastal platform. They traded a heavier, finished weight for a dramatically reduced risk of catastrophic, journey-ending damage to the sacred icon itself. Contrast this with the approach in ancient Egypt, particularly with obelisks. At Aswan, workers did an enormous amount of shaping in the quarry, smoothing three sides and creating the distinctive pyramidal top, known as the pyramidion. But the fine hieroglyphic inscriptions, the detailed reliefs that told the pharaoh's story, were almost always added later at the final destination. The obelisk was moved as a largely finished but not yet decorated needle of stone. This split the difference. They reduced the transport weight slightly by not carving the deep inscriptions, but more importantly, they protected the most politically and religiously vital artwork from the brutal realities of the hall. A chipped or scarred hieroglyph in the middle of a sacred text would be a spiritual catastrophe, so that delicate work was saved for the stable, sacred ground of the temple. Then we have the Inca, who took a third, utterly fascinating path. In the high Andes, they extracted and rough-shaped their colossal granite blocks at the quarry. These stones were moved over impossible distances as intimidating, multi-ton puzzles. The true magic, the act of fitting them together with such precision that not even a blade of grass could pass between, happened entirely on site. This method minimized transport weight to its absolute limit, moving only the essential mass, but it demanded an incredible final phase of labor. At the construction site, teams of master stoneworkers would spend months, perhaps years, slowly grinding and abutting one block against another, using stone hammers and abrasive sand until they achieved that legendary, seamless fit. The risk of transport damage was almost irrelevant, because any scars or chips on the rough surfaces would simply be ground away during this final, meticulous fitting process. Each strategy reveals a different priority. Easter Island prioritized spiritual integrity and risk reduction during the move. Egypt prioritized the protection of sacred narrative art. The Inca prioritized transport efficiency and deferred the most skilled labor to the final assembly. These were not random decisions. They were cold, calculated logistics, born from the specific challenges of their terrain, their materials, and their cultural needs. The silent, half-finished stones in these quarries are not just abandoned projects. They are frozen snapshots of a critical meeting where ancient project managers weighed the odds and made a call. The silent, precisely cut trenches and abandoned tools are a testament to more than just technique. They are the physical signature of a vast, living machine. To turn a mountain into a monument required a workforce of staggering scale, but more importantly, one of intricate organization. The quarries themselves allow us to reverse engineer this human system, not through written records, but through the undeniable logic left in the stone. The first clue is sheer volume. Look at the negative space. The amount of rock removed from a site like Aswan or Baalbek is not the work of a few hundred people over a single season. It represents thousands of worker years, a sustained effort spanning decades. This immediately rules out a simple, chaotic mob. Such a project demanded a pyramid of labor, with specialized roles layered atop one another, each essential to keeping the industrial heart beating. At the top were the master quarrymen, the true artists of fracture. These were the individuals who could read the grain of the granite, identify the hidden fault lines, and decide exactly where to place those critical wedge holes. A single miscalculation by this elite group could waste years of labor, as the crack in the unfinished obelisk tragically proves. Their knowledge was a guarded, priceless technology. Supporting them were the tool makers and maintainers. At Rano Raraku, the ground is still carpeted with thousands of basalt toki picks. These tools did not appear by magic. Their creation required a separate supply chain, mining the hard basalt, shaping it, and constantly replacing the picks that wore down against the softer volcanic tuff. This was a full-time industry in itself. Then came the vast body of laborers, the muscle of the operation, but to call them unskilled is a profound mistake. The consistent depth of the trenches, the uniform spacing of the tool marks, and the controlled fracturing of the stone all point to trained, methodical work. These individuals worked in coordinated teams, likely following rhythmic chants or drum beats to synchronize their pounding or their pulls on the ropes. They were not just lifting, they were executing a precise, physically demanding craft. Overseeing it all were the engineers and overseers, the ancient project managers. They were the ones who translated the architectural vision into a quarry plan, marking the exact outlines of future blocks on the cliff face. They coordinated the flow of materials and people, ensuring that the teams cutting new blocks did not interfere with the teams transporting finished ones. They managed the logistics of food, water, and shelter for a small city of workers stationed in a barren landscape. The quarries were not just work sites, they were temporary industrial towns. This brings us to the most critical support personnel, those who sustained life itself. Feeding thousands of workers in a remote quarry required an entire agricultural and distribution network. Water had to be hauled in or sourced locally. Bakeries, breweries, and butchery sites would have operated nearby. Evidence from worker villages near the Giza Plateau shows they received regular rations of bread, beer, and fish, indicating a state-organized supply system. This was not the work of a desperate, enslaved populace, but of a mobilized, compensated workforce. The scale and longevity of these projects suggest many of these workers might have been rotated in shifts, perhaps serving for a season or a year as a form of civic or religious duty before returning to their farms. The organization was so refined, it hints at a society that could divert a significant portion of its energy and resources toward a generational goal. The quarries, therefore, show us the blueprint of a social machine, one capable of aligning the skills of artists, the strength of laborers, and the foresight of managers into a single, earth-moving purpose. But to keep that machine running for generations required a fuel even more powerful than human muscle. It required an unshakable belief, a central idea that could justify such monumental sacrifice. The true test of ancient ambition began the moment a block was freed from the earth. It was no longer part of the mountain, but it was not yet part of a monument. It existed in a state of impossible weight, stranded in a landscape that offered no mercy. This was the ultimate logistical puzzle: terrestrial transport. How do you convince 1,000 tons of granite that it needs to go for a walk? The theories we have are not secrets of lost technology, but brilliant applications of simple physics, each method a calculated response to the brutal variables of weight, distance, and terrain. The first and perhaps most iconic method involves the sledge. Imagine a massive wooden platform built from the trunks of mighty trees, securely lashed beneath the stone. This sledge would then be pulled along a prepared track, not through raw dirt, but over a surface made slippery. Evidence from Egyptian tomb paintings and practical experiments suggest they used a lubricant, likely water or a slurry of wet clay, poured continuously in front of the runners. This reduced friction dramatically, turning a near-impossible drag into a slow, grinding but achievable slide. The manpower required was still astronomical, with teams of hundreds hauling on ropes, but the principle was sound: turn the earth into a slick, artificial river for stone. A second theory shifts from sliding to rolling: the use of wooden rollers. Here, the block rests on a series of stout logs placed perpendicular to the direction of travel. As the stone is pulled forward, the rollers rotate beneath it. Workers at the back would constantly retrieve the logs that emerged and run them to the front, creating a continuous, moving track. This method is incredibly efficient on flat, hard ground, but it presents its own nightmares on any kind of slope, where controlling the descent of a rolling multi-ton mass becomes a terrifying exercise in braking. Then there is a more dynamic, almost rhythmic technique, sometimes called walking the stone. Using massive timber levers as fulcrums, teams would lift one side of the block just enough to tilt it. They would then pivot it forward before lowering it, lift the opposite side, and pivot again. It is a painstaking, incremental process, like a colossal, slow-motion waddle. This method offers exquisite control, ideal for navigating tight spaces or uneven terrain where a sledge or rollers would be impractical. But which method did they actually use? The quarries themselves often hold the answer, not in the tools left behind, but in the very decision of where to place them. Look at Baalbek, the quarry sits on a slope above the temple site. This is not an accident, it is a declaration of intent. They plan to use gravity as their primary engine, likely sliding the stones downhill on lubricated tracks, a controlled avalanche of architecture. At Ollantaytambo, the treacherous path from the mountain quarry down to the river suggests a combination of methods, perhaps lever walking on the steepest parts, then transferring to rollers for flatter sections near the water. The terrain dictated the technology. A workforce did not master one universal technique. They mastered a toolkit of possibilities, adapting their approach to the specific challenge of each stone's journey from its birthplace to its eternal home. The monolith poised on its sledge represents only a fraction of the moving parts. For every single stone that began its journey, an entire temporary world had to spring up around it, a vast and fleeting infrastructure built solely for the purpose of moving the immovable. This is the hidden layer of megalithic logistics, the scaffolding of society that supported the stone. Think of it this way: the block itself is the cargo. But the true scale of the operation is measured by everything else that had to be created just to make that cargo budge an inch. First, the land itself had to be transformed. A path from quarry to construction site was not a simple trail. It was an engineered roadway. Trees were felled, boulders were cleared, and the earth was leveled and compacted into a firm, stable surface. In swampy areas, they built reinforced causeways of timber and stone to prevent the colossal weight from sinking into the mire. These were not mere paths. They were the ancient equivalents of heavy-haul industrial highways, designed to bear stresses that normal roads would never encounter. Then came the ramps. To lift a stone even a few feet vertically required an ingenious solution, the earthen ramp. These were not small mounds. To raise a block to the top of a growing pyramid or temple platform, they constructed colossal inclines of packed earth, brick, and rubble, sometimes running for hundreds of feet. The ramp was a temporary mountain built to conquer another mountain. Its angle was a critical calculation: too steep and the pulling teams would fail, too shallow and the ramp would become impossibly long, consuming its own volume in material and labor. Once built, it became a bustling artery with teams of workers hauling, levering, and stabilizing the stone's agonizingly slow ascent. And where did all these people live? They did not commute. At the quarry, along the transport route, and at the construction site, temporary cities emerged. These worker camps were the beating heart of the operation. Archaeologists find the remnants of barrack-style housing, communal kitchens, bakeries, and workshops for repairing tools. They find pottery shards, animal bones, and evidence of organized food distribution. This infrastructure was the life support system for the human engine. The most haunting aspect of all this is its fleeting nature. When the final stone was set, this entire temporary world was dismantled. The ramps were stripped away for their valuable fill. The worker camps were abandoned, leaving only faint stains in the soil and scattered debris. The roads, if not maintained, were reclaimed by forest and field. This is why this scale of ancient logistics often escapes us. We see the eternal stone, but we miss the vanished world of earth, timber, and sweat that made its journey possible. The permanent monument is the final act. The temporary, invisible infrastructure was the three-act play that preceded it. So we are left with a profound question. If the stones are the only permanent evidence, how can we ever truly measure the full cost of their journey? The most revealing chapters in this ancient manual of logistics are not the success stories, but the pages left abruptly blank. A quarry abandoned mid-stroke is a frozen moment of crisis, a time capsule of a problem that could not be solved. These failures are not dead ends, they are diagnostic tools, revealing the precise breaking points of ancient ambition. Each reason for abandonment acts like a spotlight, illuminating a different vulnerability in the entire megalithic system. The first and most literal breaking point is the stone itself. We saw this at Aswan with the Unfinished Obelisk. A hidden fissure, a flaw in the crystalline structure of the granite, appears during the delicate undercutting phase. In an instant, decades of planning and labor are rendered worthless. This type of failure is a stark lesson in geological humility. It shows that for all their skill in reading the rock, ancient engineers were ultimately gambling against an invisible opponent. The Earth did not always cooperate. This abandonment tells us that their system had a critical failure mode, a point of no return where the integrity of the material itself dictated the end of the project. No amount of political will or labor force could glue a shattered 1,000-ton needle back together. The second breaking point is the journey. Consider the mega block beside the stone of the pregnant woman at Baalbek. It was cut, but likely never even attempted to be moved, or the scattered giants along the Inca transport route at Ollantaytambo. These stones represent a logistical calculation that failed. The planners may have underestimated the friction, the slope, or the sheer coordination needed. Perhaps a trial move of a smaller block ended in a catastrophic, uncontrolled slide, convincing them that attempting the largest one was a guaranteed disaster. This type of abandonment reveals the outer limits of their transport technology. It marks the frontier where their mastery of physics met an equation they could not balance. It shows that ambition had a very real, very physical ceiling defined by topography and traction. Then there are the failures of the social machine itself. A quarry can be perfect, the transport route feasible, but if the society that powers it undergoes a sudden transformation, the stones will be left where they lie. Political collapse, a shift in religious power, or an economic crisis that redirects resources can halt a project overnight. The most poignant example may be Rano Raraku on Easter Island. The factory was not shut down due to a flaw in the stone or an impossible transport challenge. It was halted by a profound societal change, a shift in priorities or perhaps pressures that made the continual production of moe unsustainable. This kind of abandonment is a ghostly signal, telling us that the most complex system in the entire operation was not the ramp or the lever, but the culture that built it. When that social consensus fractures, the work stops, leaving statues half-born in the rock. Finally, we see failures of technological overreach. This is when the ambition of the design outpaces the practical execution. Perhaps an architect envisioned a block of a certain size, and the quarry masters, not wishing to contradict authority, began cutting it, only to discover too late that their methods for moving it were inadequate. This is the realm of the miscalculation where the blueprint and the reality of the workshop fatally diverged. Each of these abandoned sites, therefore, is a classroom. A crack in the obelisk teaches us about their material science and its limits. A stranded block on a mountainside teaches us about the frontier of their transport physics. A silent quarry teaches us about the fragility of the social consensus required for such endeavors. They show us that these were not infallible societies working with magic. They were brilliant, bold, and utterly human, pushing against barriers until sometimes those barriers pushed back harder. Their greatest monuments celebrate what they achieved. Their abandoned quarries, with far more honesty, show us what they dared to attempt and where the world finally said no further. The true calendar of these projects was written not in days but in seasons. We must abandon our modern idea of a continuous, year-round construction site. The rhythm of moving mountains was dictated by the ancient world's most powerful forces, the sun, the rain, and the harvest. This reveals a project timeline stretched over decades, where a single stone's journey from quarry to temple could span multiple years, a slow dance synchronized with the turning of the earth. Think of the agricultural cycle as the engine's pulse. For a society based on farming, the vast majority of the population was essential for planting and harvesting. This meant the colossal labor force needed for quarrying and transport was only available during the off-seasons. The window for monumental work was likely the dry months after the harvest, when fields lay fallow and thousands of hands could be mobilized for state service. This was not slavery in the sense we often imagine, but a form of organized civic or religious duty, a tax paid in labor. A farmer might spend a season pounding stone in the quarry or hauling ropes on a transport road before returning home in time for the next planting. This seasonal cadence imposed a natural pace on every project. A block might be cut from the bedrock in one dry season, then spend the rainy season sitting in its trench, waiting. The next dry season, teams would return to begin the perilous task of moving it, perhaps only completing a fraction of the journey before the rains came again, forcing another long pause. This stop-start rhythm is crucial to understanding the timeline. A single obelisk trip from Aswan to Luxor, a distance of over 100 miles, might have been a series of annual campaigns, with the stone progressing only a few miles each season before being parked securely for the inundation. The weather itself was a decisive project manager. Rain was the enemy of megalithic logistics. A prepared transport road, hard-packed and smooth in the dry season, would become a bottomless pit of mud under a downpour. A sledge carrying 800 tons of limestone would sink and become utterly, hopelessly stuck. The rainy season, therefore, was a mandatory shutdown period. This seasonal constraint turns our perception of time upside down. We look at the Great Pyramid and see a structure built in roughly 20 years. But if the workforce was seasonal, that means the actual number of working days was far fewer. The project managers had to achieve staggering progress during each annual window, making every dry day count with ruthless efficiency. It also means that a construction site was often a quiet, waiting place for much of the year. The partially built temple, the half-moved monolith, the idle quarry, these scenes would have been normal, expected states of being. The true scale, then, is measured in generations. A pharaoh or king would commission a temple knowing he might only see the foundation laid. His son would witness the walls rise. His grandson might preside over the final dedication. A single stone touched by the hands of a young man at the quarry might finally be set in place by the hands of his son or even his grandson. This was an act of faith in the future, a bargain struck with time itself. The monument was not just a symbol of power in the present, but a physical bridge to a future the builder would never see. So when we marvel at the precision of the fit between two massive blocks, we are not just seeing skilled stonework. We are witnessing the triumph of a system that could maintain a plan, a standard, and a purpose across the fleeting lives of countless individuals, aligning the seasons of humanity with a dream carved in stone. This generational timeline forces us to confront the ultimate question: who was holding the blueprint? Moving a mountain is not just an act of strength, it is a colossal exercise in command and control. Think of it as the world's first mega project, a puzzle of logistics, timing, and human coordination that would challenge a modern corporation. The ancient project manager did not just oversee a single work site. He orchestrated a sprawling, interdependent network of activities stretched across vast distances, and he had to keep it all moving for decades. The first and most daunting challenge was long-term planning. A pharaoh or ruler did not simply point to a hill and say, "Build here." The decision initiated a cascade of interdependent tasks that had to be sequenced years in advance. Before a single stone could be cut, surveyors had to select the quarry and map the transport route. This route then had to be built, a massive infrastructure project itself, requiring its own labor force and material. Meanwhile, at the construction site, the foundation had to be precisely laid and leveled. All of this had to happen before the first finished block even began its journey. This was not linear, it was a symphony of parallel processes, each dependent on the other's progress. A delay in road building would strand finished stones at the quarry. A mistake in the foundation would mean blocks arriving at a site that was not ready for them. The project manager had to see this entire chain in his mind, years into the future. Then came the relentless problem of resource allocation. What was the most precious resource? It was not gold, it was skilled labor. The master quarrymen, the lever teams, the ramp engineers, these were specialized roles. The manager had to decide how many of these experts were needed at the quarry versus the construction site at any given time. He also had to manage the flow of physical resources, timber for sledges and levers, ropes from hemp farms, copper for saws, food and water for thousands. This was a continuous calculation of supply and demand across a fragile, pre-industrial network. A shortage of rope in Aswan could halt the entire extraction process. A failure of the grain harvest upriver could mean hungry workers and a missed seasonal window. The manager's role was to anticipate these bottlenecks and divert resources before they became crises. This required a communication hierarchy, a nervous system for the project. In an age without radios or written reports that could travel faster than a man on foot, information moved at the speed of a runner or a riverboat. Overseers at the quarry, the transport captain on the road, and the lead architect at the temple site all had to send regular updates back to a central authority. This created a chain of command. A foreman on the ramp would report to a transport supervisor, who would report to the chief engineer, who would ultimately advise the vizier or the pharaoh's steward. Decisions made in the capital had to filter down through this chain, and problems from the field had to filter up. It was a slow, deliberate, but absolutely vital system for maintaining a single, unified vision across a 100-mile worksite. The true testament to their management skill is not that they built perfect things, but that they built incredibly complex things over unimaginable timescales without the entire endeavor collapsing into chaos. They maintained standards of precision across generations of workers. They adapted to geological setbacks and seasonal floods. They kept the faith of a society in a goal it would not see completed in a lifetime. When we look at the seamless joints of a pyramid's casing stones, we are not just seeing stonemasonry, we are seeing the final product of a flawless administrative system, one that could align the wills of thousands toward a single point in stone, across the relentless flow of time itself. The seamless joints of the pyramid are a testament to more than engineering. They are the final product of a vast and silent economy. To grasp the true foundation of these societies, we must shift our perspective from stone to sustenance. The real currency of a megalithic project was not gold or silver, it was the humble calorie. Every swing of a stone pounder, every pull on a hemp rope, every step of a 1,000-mile journey was powered by food. This transforms our understanding from a story of architecture into one of agricultural and social physics. The workers were human engines, and their fuel had to be cultivated, harvested, and delivered with the same precision as the stones themselves. So let us perform a simple, staggering calculation. Consider a single task, like extracting the unfinished obelisk at Aswan. Modern estimates suggest that just the initial trenching around that one stone, using dolerite pounders, would have required something on the order of 7 million worker hours. That is the labor of 1,000 people working 10 hours a day for almost 2 years, and that is only to outline the block, not to free it, shape it, or move it an inch. Now, a worker engaged in such brutal, constant physical labor would need a substantial daily intake, perhaps 4,000 to 5,000 calories. Multiply that by 1,000 workers, and you are looking at a daily fuel requirement of 4 to 5 million calories, just for that one crew at that one quarry. And that is merely the caloric cost of the labor itself. It does not account for the families of those workers, the administrators, the toolmakers, the guards, or the sailors who brought the grain up the Nile. This single, unfinished stone represents a mountain of bread, a river of beer, and herds of cattle that had to be mobilized solely to power its creation. This is the concept of energy accounting. The monument is not just a pile of stone, It is a mountain of converted sunlight, transformed by fields of wheat and barley into human effort, and finally into eternal architecture. Where did all this food come from? It came from an agricultural surplus so vast and reliable it could be thought of as a nation's battery. A society could only embark on a decades-long stone project if its farmers, through innovation and favorable geography, could reliably produce far more food than they themselves needed to eat. The Nile River's predictable inundation, which deposited rich, new silt across its floodplain each year, was Egypt's ultimate power source. It created a grain surplus that could be collected, stored, and redistributed by a centralized authority, the state. This surplus was the economic foundation that made everything else possible. It allowed the pharaoh's administration to support a permanent class of skilled artisans and project managers, and to summon seasonal labor from the farming population during the inundation, when the fields were underwater and farm work was impossible. The workers were not slaves starving in the desert. They were part of a sophisticated state-sponsored system. Archaeological evidence from the worker villages at Giza shows they received regular rations of bread, beer, fish, and occasionally meat. This was a calculated investment. A well-fed worker is stronger, more productive, and less likely to fall ill or revolt. The entire operation, therefore, rested on a delicate three-part balance. Fertile land created a food surplus. A strong central authority collected and managed that surplus, and that managed energy was then directed into non-food producing industrial projects that enhanced the authority's power and legacy. The quarry, the transport road, and the temple site were the visible tips of a colossal iceberg. The unseen bulk, the true foundation lying beneath the waterline, was the endless, golden sea of grain. When we look at a megalith, we are not just seeing a stone. We are looking at the physical manifestation of a society's entire economic and ecological output, crystallized into a single, eternal form. What kind of belief system could possibly justify diverting so much of a civilization's life energy into a single, silent point? But a stone's journey demanded more than just human energy. It consumed a constant, voracious appetite for materials. Every pounder that struck granite, every rope that strained under a 1,000-ton load, every lever that groaned with pressure was a consumable resource, worn down and used up in the service of moving the immovable. The true supply chain of a megalithic project was a river of secondary goods flowing toward the quarry and the transport road, a logistical ballet that had to operate flawlessly for decades. Consider the most basic tool, the dolerite pounder. At a site like Aswan, these fist-sized balls of volcanic rock, harder than granite, were the primary cutting instrument. But they did not last. Striking the unyielding granite would slowly but surely shatter them. A single worker might go through several in a single day. For a quarry employing hundreds of pounders, this meant a constant stream of new tools had to be manufactured and delivered. The dolerite itself had to be sourced from specific outcrops, often far from the quarry, shaped by other craftsmen and transported in. This created a supply chain within a supply chain, a meta-industry supporting the main event. For finer work, like sawing limestone blocks or shaping details, copper saws were essential. But copper is a soft metal. Saws would dull quickly against abrasive stone, requiring a steady supply of skilled metalworkers to resharpen, retemper, or entirely recast the blades. The demand for copper ore, charcoal for smelting, and the labor of smiths was another permanent drain on the project's resources. Then there were the ropes, the literal lifelines of transport. To move an 800-ton block, you needed ropes of immense strength and in staggering quantity. These were typically made from hemp, papyrus, or palm fiber, materials that had to be cultivated, harvested, and processed through labor-intensive methods of twisting and braiding. A single hauling team might require ropes hundreds of feet long and as thick as a man's forearm. Under such extreme tension, even the best ropes would fray, stretch, and eventually snap. The replacement rate must have been astronomical, demanding not just a one-time shipment, but a continuous, rolling production from farms and workshops dedicated solely to keeping the hauling teams supplied. Without this unbroken stream of fiber, the entire transport system would seize up in a matter of days. Finally, we have the silent enablers, the lubricants and the timber. A sledge carrying a monolith does not slide on dry earth, it grinds to a permanent halt. The solution was to create a temporary, artificial low-friction surface. Workers would pour water or a slick slurry of wet clay onto the path in front of the sledge runners. In some colder climates, evidence suggests they may have used ice. In others, animal fats could have served as a grease. This was not a trivial need. It required constant application by a team of workers walking alongside the sledge, ensuring the thin, vital layer between stone and earth never disappeared. And what of the timber, the massive levers used to pivot blocks, the rollers placed underneath them, the sledges themselves, all were made from the trunks of the largest trees available. In Egypt, where large timber was scarce, this meant importing cedar from Lebanon via great sailing ships, another layer of long-distance logistics. These wooden components also suffered immense stress, splintering, cracking, and wearing down under loads they were never meant to bear. A roller might be crushed flat after only a few dozen yards of travel, needing immediate replacement from a stockpile that had to be constantly replenished. This hidden economy of attrition reveals the project's true vulnerability. It was not a single heroic effort but a fragile, living system. A disruption in the rope supply from a poor hemp harvest, a shortage of copper due to a trade route closure, or a failure to deliver the next shipment of cedar logs could bring the entire sprawling operation to a standstill as effectively as a crack in the bedrock. The monument was not just built by people, it was built by an endless flowing river of fiber, metal, wood, and water, each drop essential to convincing the mountain to walk. The quarry was far more than a hole in the ground. It was a temporary nation, a cultural crucible where identity was forged alongside the stone. For decades, this remote landscape became home to thousands drawn from across the kingdom, from different villages, speaking different dialects, holding different local loyalties. Their shared purpose, however, was absolute: to serve the will of the God-King and move a piece of the earth. In this intense, isolated environment, something profound would have happened. The daily rhythm of shared hardship, the coordinated chant of a hauling team, the communal meal after a long day under the sun, these experiences would have slowly eroded old tribal divisions. A new, powerful identity was being built, one based not on where you came from, but on what you were accomplishing together. You were no longer just a farmer from the delta or a herdsman from the south. You were part of the crew that cut the great obelisk or the team that hauled the facing stone for the pharaoh's tomb. This shared pride in a tangible, colossal achievement created a social cohesion that mere law or decree never could. The project itself became the story that bound the society together, a story of collective power that everyone could see rising on the horizon. This temporary city also served as the ultimate theater of state authority. The project's scale was a constant, visible demonstration of the ruler's divine mandate and organizational power. The regular distribution of food rations, the presence of royal overseers, the very fact that such a bewilderingly complex operation functioned at all, reinforced the central idea that the king's order was the natural, successful order of the world. For a seasonal laborer returning to his village, the experience was transformative. He had seen the bureaucracy in action, felt the might of its logistics, and contributed to its glory. He would carry back stories not of oppression but of participation in something eternal. This transformed the monument from a symbol of top-down power into a point of shared, bottom-up pride. The finished temple or pyramid was not just the pharaoh's house, it was the place where your father and his father before him had worked. its endurance became a testament to your own lineage's contribution. The project created a living bridge between the individual and the infinite, giving every participant a stake in a legacy that would outlive them by millennia. Ultimately, these quarries and camps were factories for memory. In a world without mass media, how does a ruler embed his name and his gods into the consciousness of a scattered population? You build a story so large it becomes the landscape itself. The generations of labor required meant that a single family might have a grandfather who quarried the stone, a father who transported it, and a son who polished it in place. The monument became a family heirloom on a civilizational scale. This forged a deep cultural investment in the stability and continuity of the state that commissioned it. To threaten that state was to threaten the meaning of your own ancestors' sweat and sacrifice. The quarry, therefore, was where the abstract ideas of kingdom, religion, and legacy were made brutally, physically real. It translated belief into blistered hands and coordinated effort, transforming a population from subjects into stakeholders in a collective dream of eternity. The silent stones they left behind are not just unfinished blocks, they are the abandoned building materials of a national identity. The silent stones and scattered tools are a language, one that was never written down. This presents one of the deepest mysteries of megalithic logistics. In an era before standardized engineering textbooks or digital blueprints, how was this incredibly complex, dangerous knowledge preserved across centuries? The answer lies not in papyrus scrolls but in people. The knowledge lived in the hands, eyes, and memories of master craftsmen, transferred through a living chain of apprenticeship that turned the quarry floor into the world's most demanding classroom. Think of a young boy brought to the granite quarries of Aswan by his father, who was a quarryman. His education would not begin with theory. It would begin with carrying water for the crews, watching the rhythm of the teams, and feeling the vibration of the dolerite pounders in the earth. For years, he would be an observer, absorbing the culture of the site, the unspoken rules, and the hierarchy of skill. His first hands-on task might be helping to mix the clay slurry for the sledges, or hauling away the endless piles of stone debris. Each task, no matter how mundane, was a lesson in the ecosystem of the project. He learned the properties of materials by handling them, the sound of a good strike versus a bad one, the look of a promising vein of stone versus one hiding a flaw. The true technical knowledge, the sacred geometry of fracture, was passed down through direct, supervised practice. A master would point to a specific spot on a new block. He would show the apprentice how to feel for the grain, how to listen to the rock. The placement of the first wedge hole was a critical decision, and the apprentice would learn by doing it wrong under watchful eyes, suffering the gentle correction, not from a manual, but from a mentor who had learned the same way from his own teacher. This was knowledge encoded in muscle memory and intuition. An experienced quarryman could feel when a wedge was seated correctly, could hear the change in pitch as a fracture began to propagate cleanly. These subtleties are impossible to fully capture in words. They must be experienced. This system of apprenticeship created a living library of technique. It was incredibly effective for maintaining high standards, but it was also fragile. The chain was only as strong as its links. A plague, a war, or a sudden shift in political priorities that disbanded the skilled guilds could rupture that chain, potentially causing techniques to be simplified or lost within a generation. This fragility makes the consistency we see across centuries, like the unchanging methods used in obelisk quarrying for over 1,000 years, all the more remarkable. It speaks to a culture that deeply valued and protected these human repositories of knowledge, likely enveloping them in an aura of sacred duty. The rituals and oral traditions surrounding the work acted as a protective shell for this technical knowledge. The songs and chants that coordinated hauling teams were not just for keeping rhythm, they were mnemonic devices. The lyrics might encode counting systems, pulling sequences, or safety warnings. The ceremonies performed before cutting a major stone, offerings to the spirit of the mountain, served a profound psychological and social purpose. They marked the act as significant, dangerous, and divinely sanctioned, ensuring that everyone approached the task with the utmost seriousness and respect for the inherited protocols. The ritual framed the engineering, making the transfer of skill part of a larger, timeless story. Ultimately, the quarries themselves were the ultimate textbooks, written in 3 dimensions. A new apprentice learned not only from his master, but from the landscape of past work all around him. He could walk up to the unfinished obelisk and see, in the stone, the consequences of a misplaced wedge. He could trace the successful trenches around extracted blocks, studying the angles and depths. The quarry was an open-air archive of both triumph and failure, each scar a lesson from a previous generation. The master's role was to teach the apprentice how to read this stone library, to interpret the silent testimony of the rock. In this way, the knowledge became embedded in the place itself, waiting for the next generation of eyes to learn its language. This creates a poignant connection between the monument and the men who built it. The finished temple celebrates the divine king, but the abandoned quarry, with its tool marks and half-cut blocks, is the true memorial to the generations of masters and apprentices whose collective wisdom, passed from hand to calloused hand, made the impossible merely a matter of time. This silent, generational transfer of skill raises a fascinating parallel in human history. Centuries later, in the forests and towns of medieval Europe, another civilization would embark on a different kind of impossible dream, the Gothic cathedral. These soaring stone forests, with their ribbed vaults and walls of stained glass, represent a second peak of pre-industrial ambition. At first glance, the logistics share a familiar rhythm. Both projects mobilized thousands of skilled and unskilled workers across multiple generations. Both required a staggering agricultural surplus to feed those workers. Both were acts of profound communal faith, where a single stone laid by a grandfather might be capped by a spire placed by his grandson. The cathedral, like the pyramid, was a bargain with time, a physical prayer meant to outlive every person who touched it. Yet for all these similarities, a single, profound difference separates them, a difference that changes how we understand the ancient world. The medieval cathedral builders left behind a paper trail. We have their detailed financial records, their guild regulations, their contracts with stonemasons, and even some of their architectural drawings scratched on tracing floors. We know the names of master builders like Villard de Honnecourt. We can read their worries about budgets and their notes on engineering problems. Their knowledge began to transition from pure intuition to documented technique. The ancient quarry masters, by stark contrast, left us almost nothing in writing about their craft. Their logistics, their engineering breakthroughs, their daily calculations of force and friction, all of it resided in what scholars call tacit knowledge. This is the knowledge that lives in the hands and the eyes, the feel of a good strike with a dolerite pounder, the sound of granite about to fracture cleanly, the instinct for where to place the next wedge. It was embodied, passed directly from master to apprentice on the quarry floor, not through a manual, but through shared experience and silent observation. The cathedral's records give us a ledger of the project. The abandoned megalithic quarry gives us the project itself, frozen in mid-thought. One civilization externalized its memory onto parchment, the other embedded its memory directly into the landscape and the lineage of its craftsmen. This is why those unfinished quarries are so irreplaceable. They are the embodied records of a system that wrote its greatest manuals not on papyrus, but in stone and muscle. This silent legacy of embodied knowledge is now meeting the eyes of the 21st century. For decades, the story of these quarries was pieced together by archaeologists with measuring tapes, notebooks, and educated intuition. Today, a quiet revolution is unfolding. as a suite of advanced technologies allows us to see these ancient industrial landscapes with a clarity our predecessors could only dream of. We are no longer just observing the scars on the earth. We are mapping their hidden logic, analyzing their microscopic signatures, and tracing the invisible pathways that connected stone to sanctuary. This fusion of cutting-edge science and ancient endeavor is rewriting the logistical model, one laser scan at a time. One of the most transformative tools is LiDAR, which stands for light detection and ranging. Imagine flying a specialized scanner over a dense jungle or a rugged mountain range. The instrument fires millions of laser pulses toward the ground. These pulses penetrate the thick canopy of leaves and bounce back from the solid earth below. By measuring the time it takes for each pulse to return, a computer can construct a breathtakingly precise, three-dimensional map of the ground surface, stripping away every tree, bush, and modern building. This technology has been a revelation in places like the jungles surrounding Angkor Wat in Cambodia or the remote valleys of the Andes. What appeared to be untouched wilderness was in fact a carefully managed landscape. LiDAR reveals the ghostly outlines of ancient quarries hidden for centuries, along with the intricate network of roads, causeways, and ramps that fanned out from them. We can now see the entire transport ecosystem, understanding how planners navigated the terrain to find the most efficient, or the most spiritually significant, route from the mountain's heart to the temple's door. Back on the ground, another technology brings the intimate details of the work into stunning focus. Photogrammetry involves taking hundreds, even thousands, of overlapping photographs of an object or a surface from every possible angle. Sophisticated software then stitches these images together to create an ultra-high-resolution, measurable three-dimensional model. Applied to a quarry wall, this technique is like giving archaeologists a digital microscope. They can zoom in on tool marks and analyze their shape, depth, and pattern at a scale impossible with the naked eye. This allows researchers to distinguish between the pounding marks of a dolerite ball used for rough shaping and the finer, more deliberate strikes of a finishing tool. They can map the exact sequence of cuts made to free a block, revealing the standardized workflow of a crew that worked here 2,000 years ago. A single, abandoned wedge hole can be measured to the millimeter, telling us about the size of the tools and the precise technique used to split the stone. This turns every quarry face into a digital archive of ancient labor, where each chip and fracture tells a part of the story. Meanwhile, geological science provides the equivalent of a forensic investigation. Using portable X-ray fluorescence scanners, scientists can now take a non-destructive reading of a stone's chemical signature right at a temple site. Every quarry, even different faces within the same quarry, has a unique fingerprint, a specific blend of trace minerals embedded in the rock. By comparing the signature of a finished block in a distant pyramid to the geological maps of known quarries, researchers can now pinpoint exactly which cliff face that stone was born from. This is a logistical breakthrough. It allows us to reconstruct supply chains with forensic accuracy. We can prove that stones for a single building came from 3 different quarries, perhaps because one source was exhausted, or because a specific color of granite was needed for a sacred chamber. We can trace the movement of materials across empires, understanding trade routes and political control through the silent testimony of the stone itself. This data feeds directly into our understanding of the ancient project manager's mind, revealing a sophisticated system of resource procurement that was far more dynamic and responsive than we once assumed. The ultimate power lies in combining these tools. A LiDAR map reveals the grand transport route. Photogrammetry of a stranded block along that route shows the tool marks from its extraction. Geological sourcing confirms it came from the quarry at the route's origin. Together, they form an unbroken chain of evidence, a digital recreation of a single stone's intended journey from cradle to grave. This is not just about collecting more data, it is about asking better questions. We can now simulate the physics of moving a specific block along a specific, digitally reconstructed road. We can calculate the friction, estimate the required pulling force, and even identify the steepest inclines that would have been the most likely points of failure. Technology is allowing us to test the ancient engineers' calculations, to understand not just what they did, but the myriad alternatives they considered and rejected. The quarries are no longer static museums. They are becoming dynamic laboratories where the past is interrogated with the tools of the future, revealing the breathtaking scale of a logistics network that was, until now, only half remembered in stone. These digital tools are not just confirming old theories, they are dismantling a deep-seated cultural bias. For centuries, we have used a single, loaded word to describe these pre-industrial societies: primitive. It is a term that implies simplicity, a lack of sophistication, a stumbling toward civilization. But the evidence screaming from these quarries, now amplified by laser and algorithm, demands we retire that word forever. What we are witnessing is not primitivism, it is profound specialization. Their technology was not crude, it was exquisitely adapted. Their planning was not haphazard, it was systematically brilliant. They operated within a completely different set of constraints than we do, and within that framework, they achieved a logistical elegance that modern engineers can only admire. Consider the central challenge: moving 1,000-ton stone without diesel engines or steel cables. Our modern impulse is to apply overwhelming force to overpower the problem. Their solution was the opposite: to outsmart it. They did not fight friction, they invited water to negate it. They did not try to lift the stone, they used levers to let it pivot. They did not cut against the rock's will, they tricked it into fracturing along its own natural lines using expanding wood. This is not a story of missing technology, it is a story of hyper-efficient technology. Every tool, from the dolerite pounder to the hemp rope, was a perfect answer to a specific question posed by their environment and their material. They achieved staggering results with a minimalist toolkit because their knowledge of that toolkit's physics was absolute. Calling this primitive is like calling a master sculptor's chisel primitive because it is not a power tool. The sophistication is not in the complexity of the device, but in the depth of understanding required to wield it. This specialized knowledge was then scaled into a system, a vast and resilient one. We see this in the seasonal workforce, a brilliant synchronization of human energy with the agricultural calendar. We see it in the supply chains for rope, timber, and copper, networks that had to function for decades without a single critical failure. We see it in the project management that could maintain architectural precision across multiple generations of workers. This is not the behavior of a simple society. It is the hallmark of a highly complex, deeply organized civilization with a remarkable capacity for long-term collective action. Their system was built on different principles than ours, perhaps less focused on individual speed and more on communal endurance, but it was a system nonetheless, and it worked on a scale that is difficult for us to fully comprehend. The paradigm shift, then, is this: we must stop measuring them by our yardstick. Their greatness is not a lesser version of our own, it is a parallel achievement. They mastered a world of stone, muscle, and seasonal time. We master a world of silicon, electricity, and digital time. The unfinished quarry is the ultimate argument against condescension. That cracked obelisk at Aswan is not a symbol of failure, but a fossilized moment of high-stakes problem-solving. The stranded block on an Andean slope is not proof of folly, but a marker of the calculated risks inherent in their ambition. These sites force us to replace primitive with precise, to replace accidental with orchestrated. They show us cultures that looked at a mountain and did not see an obstacle. They saw a partner in a conversation that would last for generations. Their legacy is not that they built big things with simple tools, but that they built impossible things with an intelligence so seamlessly woven into their culture and landscape that its full brilliance is only now, with our own advanced tools, coming completely into focus. Even with our modern tools and theories, the quarries guard their deepest secrets. For all we have mapped and measured, fundamental questions linger in the silent spaces between the tool marks, questions that challenge our understanding of ancient coordination. The most persistent mystery is the final act of transport for the very heaviest stones. We have compelling theories, sledges on lubricated tracks, rollers, and lever walking. But the physics of moving a 1,000-ton block like the stone of the pregnant woman at Baalbek remains at the edge of plausibility. Could a lubricated path truly support such concentrated weight without the sledge digging itself a permanent grave in the earth? How many ropes woven from what material would not snap under the strain? Experimental archaeology has shown that our proposed methods work on a scale of tens of tons, but scaling that up by a factor of 20 or more enters a realm where the laws of physics become unforgiving. A slight unevenness in the road, a momentary lapse in the application of water or grease, and the entire endeavor would freeze. The quarries show us the starting line with perfect clarity, but the race itself, especially for the true giants, is a blur of possibility. This leads directly to a second, more abstract puzzle, the mystery of synchronization. How did a project manager, without digital calendars or instant communication, maintain a precise schedule across a network that stretched for hundreds of miles and decades in time? Consider the logistics. A block is successfully cut at the quarry in year 5. It begins its journey, a slow, seasonal crawl. Meanwhile, at the distant temple site, the foundation must be ready to receive it at the exact moment it arrives years later. Other blocks are coming from different quarries on different timelines. The ramp to lift them must be built to the correct height at the correct moment. This is not just about moving stone, it is about moving information. How did they forecast with such accuracy? Did they use a system of messengers on predetermined routes, carrying clay tablets that said, "The obelisk has passed the 3rd canal, expect it at the temple in 2 seasons"? Was there a master calendar tied to the stars and the flood of the Nile that dictated not just when to plant crops, but when to order the next batch of ropes from the delta, or when to shift a crew from quarrying to ramp building? The flawless fit of the stones suggests a plan that was not just brilliant but resilient, able to absorb delays and adapt without losing the grand vision. The mechanism of this ancient project management software, written in human memory and ritual, is a code we have yet to fully crack. Finally, the global scale of this phenomenon presents perhaps the most tantalizing question of all. We see the same megalithic logic in Egypt, Lebanon, Peru, and Easter Island, a logic of remote quarries, controlled fracture, and Herculean transport. So, were these cultures tapping into a shared, universal principle of large-scale logistics, a kind of innate human engineering instinct that emerges when a society decides to build for eternity? Or did each civilization, in glorious isolation, invent this incredibly complex system from scratch, independently converging on the same solutions to the same physical problems? The evidence is a fascinating puzzle. The techniques are similar in concept but differ in fascinating details: the specific stone, the exact tools, the choice of when to sculpt. This suggests independent innovation, a testament to the universal human capacity to solve colossal problems. Yet, the underlying pattern of thought, the willingness to commit generations to a single task, the ability to organize thousands, the drive to convert a mountain into a message, feels like something deeper than mere coincidence. It speaks to a shared human response to certain conditions like political stability, agricultural surplus, and a unifying belief system. Perhaps the quarries are not evidence of a lost global civilization, but of a recurring chapter in the human story, a chapter where societies reach a peak of collective confidence and choose to inscribe their identity not on parchment, but on the very bones of the planet. The unfinished stones do not answer this for us. They simply ask across the silence of millennia, what is it within us that looks at a mountain and sees not an end but a beginning? The unfinished quarries scattered across our world are far more than archaeological curiosities. They are the Rosetta Stone for deciphering the true scale of ancient ambition. When we stand before a perfect pyramid or a serene temple, we witness the final, polished answer. But in the chaotic, scarred landscape of the quarry, we are given the working, the complete and messy equation of how that answer was derived. These abandoned workshops reveal that the greatest marvel was never the mystical placement of a single, massive stone. The true wonder was the sustained, coordinated human effort across generations, the vast, invisible machinery of logistics that made the stone move in the first place. This was a symphony of organization conducted over decades, requiring the precise alignment of geology, agriculture, engineering, and social will. It shows us cultures that could think in centuries, that could align the seasonal rhythms of farming with the generational task of moving mountains. Their ingenuity was not in defying physics, but in partnering with it, using water, wood, and lever to persuade the earth itself to cooperate. So the next time you look upon an ancient monument, try to see beyond the majesty of the finished form. Look for the ghost of the quarry. See the thousands of hands that pounded the stone, the miles of rope that strained against impossible weight, the seasonal armies that transformed sunlight and grain into a collective dream of eternity. See the hidden industry, the breathtaking logistics, and the quiet, persistent proof that humanity's most enduring structures are built not from magic, but from the profound, organized power of a shared purpose.